In the vast, chaotic theater of the universe, there is a distinct and unsettling suspicion that someone has lazily copy-pasted the fundamental building blocks of reality. Look closely at the device in front of you. Now, imagine looking into the heart of a dying star at the edge of the observable cosmos. The electrons coursing through your circuits and the electrons screaming in the stellar plasma are not just similar, they are terrifyingly identical. They share the exact same mass to the infinite decimal, the exact same electric charge, and the exact same intrinsic spin. In a reality defined by entropy and infinite variation, where no two snowflakes or fingerprints are alike, every single electron in the cosmos is a perfect carbon copy of every other. This is not a trivial coincidence. It is a deep statistical anomaly that screams for an explanation. Why would nature, in its boundless creativity, manufacture 10 to the power of 80 distinct particles using a single, rigid mold? Standard physics accepts this as a fundamental postulate, the principle of indistinguishability. We are told to accept that electrons are simply fungible, like currency. $1 is as good as another. But in the spring of 1940, the brilliant theoretical physicist John Wheeler wasn't satisfied with just because. He picked up the phone and called his doctoral student, a young Richard Feynman, with a revelation that would sound like the ravings of a madman to anyone outside the high temple of theoretical physics. Wheeler didn't propose that electrons were mass-produced in a factory at the dawn of time. He proposed something far more elegant and disturbing. He suggested that the reason all electrons look exactly the same is that there is, in fact, only one electron in the entire universe. To understand how this is geometrically possible, we have to transcend our limited, linear perception of time. We perceive our lives as a series of moments, moving from birth to death like a bead sliding along a string. In physics, we call this a world line, the path an object traces through the four-dimensional block of spacetime. If you were to map your life, it would look like a single, jagged line stretching from the past into the future. But Wheeler imagined a world line that didn't just go straight. He imagined a single, continuous thread tangled in a four-dimensional ball of yarn, weaving back and forth, knotting and looping through the fabric of history. Imagine the universe not as a boundless void filled with trillions of particles, but as a single monumental box of space and time. Inside this box, that solitary electron begins its journey at the Big Bang. It travels forward through time to the end of the universe, witnesses the heat death, and then, rather than ceasing to exist, the electromagnetic fields of the cosmos force it to turn around. It reverses its trajectory through time, traveling all the way back to the beginning. It then turns again, heading forward. It repeats this zigzag marathon billions upon billions of times. The complexity of this single line is so dense that it fills the entire volume of spacetime. What we perceive as reality is just a cross-section of this four-dimensional tangle. Imagine taking a sharp knife and slicing through a massive, chaotic ball of string. On the face of the slice, you wouldn't see the long, continuous thread. You would see hundreds of little severed points, distinct and separate. To a three-dimensional observer trapped in the now, that is exactly what we see. We look around and count trillions of electrons scattered across galaxies, stars, and atoms. We think they are a swarm. But we are merely seeing the billions of times that one solitary traveler has intersected with our specific moment in history. This hypothesis, known as the One-Electron Universe, solves the problem of identity in a single stroke. Of course they are all identical. Of course they share the same mass and charge. You cannot distinguish them because you are looking at the same entity just viewed at different stages of its eternal, looping journey. It implies a connectivity to the cosmos that borders on spiritual, yet is grounded in the rigid geometry of relativity. It suggests that the electron bonding the carbon atoms in your DNA is the exact same particle that is currently fueling the fusion reactions in Alpha Centauri, separated only by the length of the string connecting them through the deep past or future. It is a concept that turns the universe from a collection of parts into a single, self-interacting knot. Building on that tangled web of spacetime, we have to confront the mechanics of the turn. How does a particle simply reverse in time? And what does that look like to us, the observers trapped flowing in the forward direction? This is where Wheeler's wild theory stumbles accidentally into one of the most profound discoveries of 20th century physics. When an electron travels forward in time, we perceive it as normal matter, negatively charged, with standard mass. But Wheeler and Feynman realized that if you take the mathematical equations for an electron and flip the time variable, making the particle move backward, the geometry manifests a physical inversion. The negative charge flips to positive. To an observer watching this event, it wouldn't look like a particle moving backwards. We can't see backwards time. Instead, we would see a particle with the same mass but an opposite positive charge moving forward. We would see an antiparticle. In this case, the positron. This was the stroke of genius in the one-electron universe theory. It provided a tangible geometric explanation for the existence of antimatter. Antimatter isn't some exotic, magical substance. It is simply normal matter that has turned around and is heading back towards the Big Bang. Visualize the knot in the world line. Picture the electron cruising along through the 20th century. Suddenly, it interacts with a high-energy photon, a gamma ray. In spacetime diagrams, this interaction knocks the electron off its forward course and sends it careening backward into the past. To us, watching in the laboratory, we see something different. We see a photon spontaneously creating a pair of particles, one electron and one positron. This is pair production, a phenomenon we verify in particle colliders every day. Wheeler's theory interprets this not as creation, but as a U-turn. The electron was always there, it just doubled back. Conversely, when an electron and a positron collide, they annihilate, releasing a burst of energy. In the one-electron view, this is just another corner. The backward-traveling section meets the forward-traveling section, and they connect, creating a continuous loop that heads off into the past. The particle didn't die, it just rounded a corner in time and left our immediate view. However, beautiful theories are often murdered by ugly facts. There is a glaring hole in the one-electron universe that Feynman immediately pointed out during that fateful phone call. If this single particle is weaving back and forth, looping from the beginning of time to the end and back again, there should be a symmetry. For every section of the thread going forward, there must be a section going backward to return to the start. This means the universe should contain an exactly equal amount of matter and antimatter. But when we look out into the universe, we see a massive imbalance. We are surrounded by electrons. They are in our atoms, our rocks, our air. Positrons, on the other hand, are incredibly rare, found only in cosmic rays or created fleetingly in accelerators. If the theory were true, half the universe should be antimatter. We should be annihilating instantly. Wheeler, in a desperate bid to save the idea, suggested that perhaps the positrons were hiding in plain sight, disguised as protons. But this couldn't hold up. Protons are nearly 2,000 times heavier than electrons. The symmetry was broken. The math didn't balance. Yet, while the literal one-electron theory was largely discarded as a physical reality, its ghost haunts modern physics. The mathematical framework Feynman developed from this idea, treating antiparticles as matter moving backward in time, became the bedrock of quantum electrodynamics. It is the standard method physicists use today to calculate the interactions of light and matter. The one-electron universe remains one of the most successful wrong ideas in history. It taught us that our intuition about time, identity, and distinctness is fragile. Even if there are trillions of electrons, the fact that they could be one tells us something profound about the fundamental unity of the quantum field. We are left with the lingering, eerie thought that separation might just be an illusion of our perspective, a trick of the light projected by a single eternal dancer moving across the stage of eternity.